Tonight, we need to talk about something that has quietly shaken the foundations of modern cosmology. Not a theory, not a simulation, not a prediction, a real observation made by the most powerful space telescope humanity has ever built that caused one of the world's most respected Nobel Prize-winning physicists to stand in front of a room full of scientists and say out loud that we may be living in a fundamentally different universe than the one we thought we understood. And the strangest part, he wasn't being dramatic. He was being careful. For decades, we believed we had the universe figured out. Not perfectly, not completely, but well enough. We had equations that predicted how fast the universe should be expanding. We had measurements. We had confirmation. The whole edifice of modern cosmology was built on a number called the Hubble constant, and that number told us everything. It told us how old the universe was, how large it was, how it evolved, and where it was going. Scientists were so confident in this number that many considered cosmology to be, in a sense, a finished project. The big questions had been answered. The remaining work was just filling in details. Then the James Webb Space Telescope opened its eyes, and everything we thought we knew began to unravel. Let's start from the beginning, because to understand how strange this discovery truly is, you need to understand what came before it. You need to understand the number that started this crisis, the people who measured it, and why their disagreement is not a minor technical dispute but a genuine fracture running through the heart of physics itself. The story begins not with Webb, but with a man named Edwin Hubble working at the Mount Wilson Observatory in California in the early 20th century. In 1929, Hubble made one of the most important discoveries in the history of science. He discovered that the universe is expanding. By studying distant galaxies, Hubble noticed that the farther away a galaxy was, the faster it appeared to be moving away from us. This relationship between distance and recession speed became known as Hubble's law, and the rate at which the universe expands became known as the Hubble constant, denoted by the letter h0. The Hubble constant is measured in kilometers per second per megaparsec. 1 megaparsec is about 3.26 million light-years, so the Hubble constant tells you how many kilometers per second faster a galaxy is moving away from us for every 3.26 million light-years of distance between us and that galaxy. Hubble's original measurement was wildly off by modern standards. He got about 500 kilometers per second per megaparsec, which implied the universe was only about 2 billion years old. That was obviously wrong even then because geologists knew the Earth itself was older than that. Over the following decades, astronomers refined the measurement again and again. Better telescopes, better instruments, better understanding of the cosmic distance ladder, the chain of techniques used to measure distances across the universe. By the time we entered the 21st century, the measurement had converged on something close to 70 kilometers per second per megaparsec, give or take. The universe was about 13.8 billion years old. Everything fit together neatly. The model worked. But then two different groups of astronomers measured the Hubble constant using two completely independent methods, and they got different answers. Not slightly different, not within the margin of error different. Significantly, stubbornly, incompatibly different. And the gap, instead of closing as measurements improved, only got wider. This discrepancy became known as the Hubble tension, and it has been quietly tearing cosmology apart for years. Here is how the two measurements work, because the method matters enormously. The first method looks at the early universe. In the years after the Big Bang, the universe was a hot, dense plasma of matter and radiation. Sound waves traveled through this plasma, creating patterns of higher and lower density. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, this plasma became transparent and the sound waves froze in place. That frozen pattern is called the cosmic microwave background, the afterglow of the Big Bang that we can still detect today as a faint glow of microwave radiation coming from every direction in space. By carefully measuring the patterns in the cosmic microwave background, physicists can extract the Hubble constant with extraordinary precision. This method is essentially using the early universe as a ruler. The European Space Agency's Planck satellite did this measurement with astonishing precision and got a Hubble constant of about 67.4 kilometers per second per megaparsec. The second method looks at the nearby universe. Astronomers use a chain of distance measurements, starting with nearby objects whose distances can be measured directly, then stepping outward to use those as calibrators for measuring farther objects. At each step, a different technique is used. Parallax for nearby stars, Cepheid variable stars for intermediate distances, Type 1a supernovae for the greatest distances. These supernovae, known as standard candles because they all have roughly the same intrinsic brightness, can be seen across billions of light-years. By comparing their apparent brightness to their known intrinsic brightness, their distances can be inferred. Using this method, a team called the SHOWS collaboration got a Hubble constant of about 73 kilometers per second per megaparsec. That's the team led by Adam Riess, who won the Nobel Prize in Physics in 2011 for discovering that the expansion of the universe is accelerating. This is not a junior researcher making a careless mistake. This is one of the most careful, meticulous measurements in astronomy, checked and rechecked for years. The two numbers, 67.4 and 73, sound close, but in physics, the gap between them is enormous. The measurements are so precise that the probability of this discrepancy occurring by chance is less than 1 in a million. Something is genuinely wrong. Either one of the measurements has a systematic error, or our model of the universe is fundamentally incomplete. For years, most cosmologists assumed it was a measurement error. Someone was making a mistake somewhere. The instruments were miscalibrated. The distance ladder had a systematic flaw. It would be sorted out. Don't panic. Then the James Webb Space Telescope launched. Webb was supposed to solve the Hubble tension. That was one of the explicit goals of the mission. Webb's infrared cameras could see Cepheid variable stars with unprecedented clarity, even in distant, crowded galaxies. Webb could check the Cepheid measurements that the Hubble Space Telescope had made, verify or correct them, and settle the debate. The expectation was clear. Webb would find a mistake in the Hubble telescope's measurements, the two values would converge. The Hubble tension would dissolve. Everyone would go home satisfied. That is not what happened. Webb looked at the Cepheid stars. It confirmed Hubble's measurements. Not approximately, not close enough to explain the tension. Webb looked at the same stars, with far better resolution, far less contamination from surrounding stars, far cleaner data, and got the same answer that Hubble got. 73, still 73. The Cepheids are not wrong. The distance ladder is not broken. The supernovae measurements hold up. This is where Adam Riess, the Nobel laureate, stood up and said the words that sent a wave of unease through the cosmology community. He said that the measurements appear to be correct on both ends, that both the early universe measurement and the late universe measurement are producing accurate results. And if both measurements are accurate, it means that the universe has somehow been expanding at different rates at different times in ways that our current model of physics cannot explain. It means, in his words, that this may be a different universe than what we thought. Think about what that means for a moment. The model we use to understand the universe, the lambda-CDM model, which stands for lambda cold dark matter, is the most successful cosmological model ever developed. It accounts for the large-scale structure of the universe, the patterns in the cosmic microwave background, the abundance of elements created in the Big Bang, the formation of galaxies, and dozens of other observations all at once. It has been tested and confirmed thousands of times. It is the framework through which physicists understand everything, and it cannot explain a universe where the Hubble constant is simultaneously 67.4 and 73. Both cannot be right in a universe governed by our current understanding of physics. Something must be missing from the model, something fundamental, something that changes the expansion rate of the universe in a way we have not accounted for. The possibilities that physicists are now considering are genuinely astonishing. And this is where the story gets even stranger. The first possibility is that dark energy is not what we think it is. Dark energy is the mysterious force or field that is causing the expansion of the universe to accelerate. It was discovered in 1998, earning the Nobel Prize for Saul Perlmutter, Brian Schmidt, and Adam Riess. In the Standard Model, dark energy is represented by the cosmological constant, a fixed, unchanging energy density that permeates all of space. It is a constant. It does not change over time. It does not vary from place to place. It just is. But what if dark energy is not constant? What if it evolves over time? What if, in the early universe, dark energy behaved differently than it does today? If the energy density of dark energy was slightly different in the past, it could change the predicted expansion rate of the early universe in ways that might reconcile the two Hubble constant measurements. This idea goes by various names: dynamical dark energy, quintessence, phantom dark energy. None of these are proven, none are even firmly established. But they are real possibilities that are now being taken seriously in a way they were not before Webb confirmed the Hubble tension. And here is the haunting part. In early 2024, a new dataset from the Dark Energy Spectroscopic Instrument, a survey that mapped millions of galaxies in extraordinary detail, found hints that dark energy may indeed be changing over time. Not a confirmed detection, not a definitive measurement, but a hint, a whisper. A statistical signal that has physicists sitting forward in their chairs and reading the data very carefully. But it gets even stranger. The second possibility is that there is something wrong with our understanding of the early universe. Remember, one of the two Hubble constant measurements comes from analyzing the cosmic microwave background, the afterglow of the Big Bang. That measurement relies on a precise model of what the early universe looked like, how matter and radiation interacted, and how sound waves propagated through the primordial plasma. If there is some ingredient missing from that model, some particle species or interaction that we have not accounted for, it could shift the predicted Hubble constant. One candidate is called early dark energy. In this scenario, dark energy was not always as negligible as it is today in the early universe. If there was a period before the cosmic microwave background was released when dark energy contributed a small but meaningful fraction of the universe's energy budget, it would have changed the expansion rate of the early universe slightly, and that small change in the early universe would propagate forward in time, shifting the predicted Hubble constant upward from 67.4 toward 73. It is an elegant idea, and it is actively being tested with new data. Another candidate involves something called extra-relativistic species. In the early universe, the number of different types of particles present affects how quickly the universe expanded. In our current model, we account for photons, electrons, and 3 species of neutrinos. If there were additional light particles, additional neutrino species, or other relativistic particles, they would have contributed to the expansion rate of the early universe, shifting it upward. This is referred to as an increase in the effective number of relativistic species, or NF. And here is the fascinating thing. Webb is now measuring this parameter too. Webb has been observing the cosmic microwave background at higher resolution than any telescope before it, and it is probing NF with unprecedented precision. Any detection of extra-relativistic species would be revolutionary. It would mean there are undiscovered fundamental particles shaping the evolution of the universe. The third possibility is the most unsettling of all. What if there is no solution? What if the two measurements are both correct in their own respective contexts, and the universe genuinely has a different expansion rate depending on which era you are measuring? This would not just be a problem for cosmology. It would be a problem for fundamental physics. It would mean that the laws of physics themselves are not as universal as we assumed, that space and time behave differently in the early universe than they do today, that the constants of nature might not be constant. This possibility sounds radical. It sounds like science fiction, but it is being discussed in peer-reviewed journals by the most respected physicists in the world. Because when your most precise measurements give incompatible results, and you have checked everything you can think of to check, you have to start considering that the laws you are using might be incomplete. And this brings us to what James Webb has been doing beyond just measuring the Hubble constant, because that is only the beginning of the strange things it has found. In the first year after Webb began science operations in 2022, it detected something that no one was prepared for. Galaxies, massive, fully formed, surprisingly mature galaxies, at a distance that put them in the first few 100 million years of the universe's existence. Galaxies that, by all rights, should not have been there. In the standard model of cosmic evolution, the first stars did not form until about 100 to 200 million years after the Big Bang. The first galaxies assembled gradually over hundreds of millions of years, growing through mergers and accumulation of material over cosmic time. The galaxies in the early universe should be small, irregular, messy, still in the process of assembling themselves. That was the prediction. That was what generations of cosmological simulations had shown. Webb looked at the early universe and found something different. It found galaxies that appeared to already be massive, already structured, already comparable in stellar mass to the Milky Way, existing just a few 100 million years after the Big Bang. Some of these galaxies appeared to have already completed most of their star formation and entered a quiet, settled phase. They looked old, they looked evolved, they looked like they had been there for much longer than the universe had existed. Astronomers nicknamed these objects universe breakers, not because they literally break the universe, but because they broke the models. The simulations that had been run for decades, the models that predicted what the early universe should look like, did not produce these objects. They could not produce these objects. The galaxies were forming stars too efficiently, too early, too quickly, as though some process was operating in the early universe that was far more effective at building structure than anything in the standard models. The initial reaction was cautious. Maybe the distances were wrong. Maybe what looked like massive early galaxies were actually closer, less extreme objects. Maybe the photometric redshifts, the technique used to estimate distances from colors alone, were misleading. Follow-up observations were needed to confirm the distances spectroscopically by actually measuring the precise wavelengths of emission and absorption lines from these objects. Those follow-up observations came, and they confirmed the distances. These objects are real. They are where Webb says they are, and they are as massive as the photometry suggested. The universe breakers held up under scrutiny. This sent theorists scrambling. If galaxies can form this quickly in the early universe, something must be different about the conditions in the early universe. One possibility is that the first stars were different. In the current model, the very first stars, called population 3 stars, formed from pure hydrogen and helium, with no heavier elements. These metal-poor stars should have been extremely massive, burning hot and fast, but they should not have been forming in vast numbers early enough to build the galaxies Webb is seeing. But what if the efficiency of star formation was much higher in the early universe than our models predict? What if the gas in early galaxies converted into stars at a much greater fraction than it does in galaxies today? Modern galaxies are actually quite inefficient at turning gas into stars. Less than a few % of a galaxy's gas is converted into stars at any given time. The rest is expelled by supernova winds, heated by radiation, or simply too diffuse to collapse. If the early universe operated differently, if the gas was colder or denser or configured in ways that allowed much more efficient star formation, then massive early galaxies become possible. And here is what makes this moment in science so extraordinary. It is not that we are discovering we were completely wrong about everything. It is that we were right enough to build an instrument powerful enough to find the places where we were wrong. The James Webb Space Telescope is the product of 30 years of planning, billions of dollars of investment, and the coordinated effort of thousands of scientists and engineers across multiple countries. And the thing it has done is look at the universe with enough precision to find the cracks in our understanding. That is a profound thing. The better your instruments, the stranger the universe looks. And then there is the question that hovers over all of this like a ghost in the background. The question that no one is quite saying out loud, but that everyone is thinking. If our model of the universe is wrong in these ways, how wrong is it? Are we talking about a minor correction, an adjustment to a parameter here, a new particle there, something that preserves the essential structure of our understanding while filling in gaps? Or are we talking about something deeper, something that would require rethinking fundamental assumptions, something that would reshape not just cosmology but physics? The Hubble tension is a 4.5 sigma discrepancy. The early galaxy problem is multiple sigma discrepancy. These are not noise, these are signals, and the history of science says that when careful measurements by careful scientists produce results that do not fit the model, you should pay attention, because sometimes the model is wrong. There is something both humbling and exhilarating about this moment. Humbling because it reminds us that despite everything we have achieved, despite all the equations and telescopes and Nobel Prizes, we are still looking at the universe with incomplete eyes. We are still missing something large, maybe many large things. Exhilarating because it means we are not done. The great discoveries are not behind us. The map is not fully drawn. There are still continents of understanding waiting to be found. Here is the thing about science that people sometimes forget. The goal is not to confirm what we already believe. The goal is to find the truth. And sometimes the truth is inconvenient. Sometimes the truth requires you to sit in a room full of brilliant people and say, honestly and with precision, that you do not understand what you are seeing. That the data does not fit the model. That something is wrong with the picture. That requires courage. It requires honesty. And it is exactly what is happening in cosmology right now. Adam Rice measuring the Hubble constant and finding 73 when the model predicts 67. Webb confirming that Cepheid measurements are correct and the tension is real. Theorists working through the night considering early dark energy, extra particle species, warm dark matter, new physics. Scientists analyzing the spectra of distant exoplanet atmospheres looking for the chemical signatures of life. This is not a crisis in science. This is science working exactly as it is supposed to work. Precise measurement, honest reporting, rigorous debate, pursuit of truth even when the truth is uncomfortable. And what is the truth, as best we can tell right now? The truth is that the universe is expanding faster than the standard model of the early universe predicts. The truth is that galaxies and large-scale structures formed faster than our simulations produce. The truth is that dark energy might be changing over time. Dark matter might be more complex than we assumed, and the first moments of the universe's existence might contain physics we have not yet discovered. The truth is that we are surrounded by mysteries that our best instruments have only just begun to probe. But perhaps the deepest truth is this. You are alive at the exact moment in human history when we built something powerful enough to see these mysteries. You are alive when the Hubble tension became undeniable, when the universe breakers were found, when the first possible biosignature was detected in an exoplanet atmosphere, when a Nobel laureate looked at the data and said, with careful scientific precision, that this might be a different universe than we thought. These discoveries are happening now, not in some distant future. Not in a textbook from 50 years ago. Now. And the telescope doing this is orbiting the Sun right now, 1,000,000 miles from Earth, continuing to collect photons, building up its observations, feeding data to scientists around the world who are reading it carefully and asking harder and harder questions. Zoom out for a moment. Not just from Earth, not just from the solar system. Zoom out to the scale where galaxies are specks of light, where the observable universe is a sphere 93 billion light-years across containing 2 trillion galaxies, where dark matter threads the entire structure like an invisible web, where dark energy is pushing everything apart at an accelerating rate that we cannot fully explain. Now zoom in, back to this planet, back to these scientists, back to these instruments of glass and metal and silicon that we have launched into space and pointed at the oldest light in the universe. Something extraordinary is happening. A species that has existed for perhaps 300,000 years, on a planet that has existed for 4.5 billion years, orbiting a star that is one of 2 trillion stars in the observable universe, has developed the technology and the intellectual framework to ask real questions about the structure of all of reality. And the universe, for the first time in its 13.8 billion year history, has something looking back at it with comprehension. That is not a small thing. That is possibly the most remarkable thing that has ever happened in the observable universe, or at least the most remarkable thing we know of. And the answer to what Webb is finding, what the Hubble tension means, what the early galaxies tell us, what the possible biosignature signals, these answers will define our understanding of reality for generations. The universe has always been out there, vast and indifferent and astonishing. But for the first time, we have eyes powerful enough to see the places where our map is wrong. And the bravest thing a scientist can do is look at the data and say simply that we need a better map. What kind of universe do we actually live in? The honest answer, for the first time in decades, is that we are not entirely sure. And that is not a failure. That is the beginning of the next great chapter. If you find yourself looking up at the night sky a little differently after tonight, wondering what else might be up there that does not fit the models, wondering what questions Webb has not yet answered, wondering what discoveries are being read right now in data that has already been collected but not yet fully understood, then you understand exactly what it feels like to be a scientist in this moment. Welcome to the edge of the map. The most interesting territory has always been the place where the known world ends and the unknown begins,